So, what we're looking at today, this is more than just a concept or a component. It's the actual architectural blueprint for a next-generation propulsion system. This is the engineering spec, designed from the ground up, that's really set to unlock the future of regional air travel.
Okay, let's break this down. To really get our heads around this system, we're going to walk through 5 key areas. First, we have to understand the fundamental problem we're solving. Then, we'll dive into our architectural solution. From there, we'll look at its operational modes, the non-negotiable safety measures baked in, and finally, the rigorous path we take to prove it's airworthy.
All right, let's start with the big one. This is the core challenge that every single pure electric aviation program is smashing its head against. And this isn't just an engineering hurdle, it's a hard limit that's being imposed by the laws of physics.
And this chart really just says it all, doesn't it? Even when you account for the fact that a heat engine isn't perfectly efficient, jet fuel's still packing about 40 times more energy per kilogram than even our best, most advanced lithium-ion batteries. You just can't get around that. It creates this unavoidable physical wall for long-range, commercially viable electric flight. So, the question becomes, how do we get over that wall? The answer isn't to sit around and wait for some miracle battery to fall out of the sky. The answer is to engineer a smarter power architecture right now. Now this diagram gets right to the heart of the system's elegance. It's what we call a series parallel hybrid. You can see it's a dual path design. You got the mechanical path, that's where we use a thermal engine for what it's best at, efficient, continuous power for cruise. But then you also have the electrical path, where batteries do what they do best, delivering massive amounts of quiet power on demand for things like takeoff and landing. It's all about using the right tool for the job for each phase of flight. So we have this clever architecture, but how does it actually work in practice? Well, let's get into the operational side of things and see how this system intelligently adapts throughout an entire mission. It isn't a static system, it's dynamic. It reconfigures itself on the fly for peak performance. The brains of the operation are managed through these 5 distinct modes. And here's the key. The pilot isn't sitting there flipping switches. The vehicle control unit is handling everything, automatically selecting the absolute best mode for any situation, whether you're taking off quietly over a city or cruising efficiently for hundreds of kilometers. So let's just walk through a typical flight to see how this all comes together. We lift off the ground silently, using only the batteries in E-hover mode. As we climb out, we transition to series mode. The engine kicks on, but it's just acting as a super efficient generator. And then, for the long cruise portion of the flight, a clutch engages, and we lock into that direct mechanical path in parallel mode. That's where you get maximum range and efficiency. Okay, now for what is, without a doubt, the most critical part of any aviation system. Look, performance and efficiency are great, but they mean nothing without safety. So let's really dig into how this architecture is designed from its very DNA to be fundamentally fail-safe. Our core safety philosophy is built on this principle of dissimilar redundancy. And that was a very deliberate architectural choice. By having 2 power sources that fail in completely different ways, one running on fuel, the other on electrochemistry, we basically design out the risk of a single problem, like a software bug or a bad batch of cells, taking down the entire aircraft. And this slide just illustrates that philosophy perfectly. Take a look at scenario A. Let's say the entire electrical system goes dark. Battery, motors, generator, everything. No problem. The thermal engine is still mechanically connected to the props. You're still flying. Now flip that. Look at scenario B. The engine fails completely. Instantly, the battery system takes over, providing more than enough power to the motors to complete the mission and land safely. Everything we've just talked about builds towards this one non-negotiable number. This is the target set by the strictest EASA certification standards. The probability of a catastrophic failure has to be less than 1 in a billion flight hours. Every single design choice is driven by hitting that number.
So, having a robust design on paper is one thing. But how do you actually prove it's safe? How do you prove it's airworthy? That's achieved through a process called the V model, which is the gold standard in the industry.
The V model is how we progressively squeeze every last drop of risk out of the system. We start in a pure software simulation. Then we start plugging in actual hardware. And that process culminates in what we call the Iron Bird. This is a full-scale, ground-based test rig with all the flight hardware bolted down. It lets us run thousands of flight hours and throw every failure you can possibly imagine at it, all safely on the ground long before the real aircraft ever leaves the hangar. So, at the end of the day, what does all this mean? This robustly engineered system, it's not just a clever technical solution. It's the commercial key. It's what makes those routes in the 150 to 600 kilometer sweet spot profitable. This is the piece that unlocks the entire regional air mobility market, a market that, frankly, pure electric designs just can't reach.
So by solving these fundamental challenges of range and safety, this technology makes regional air mobility not just possible, but actually commercially viable. It's not science fiction anymore. And that leaves us with one final, really exciting thought. Now that we can do it, where are we going to go first?